All right, welcome everyone. Thank you for coming. This is day one of our 2025 GRASP Research Overview Days. We have a really packed schedule today, so I ask all of our speakers to please stick to your allotted time. You'll have a total of 6 minutes for your presentation. I'll be in the front row, or Charity will be in the front row to give you a warning when you have 2 minutes left and 1 minute left. And then whoever is the next presenter, I'll also ask that you line up at the podium so that when it is your turn, you are ready to go promptly. Our first speaker today is Dr. CJ Taylor. Whenever you're ready, the floor is yours, and I will start your time.
Hey, fantastic. All right. Okay, welcome everybody. My name is CJ Taylor. I'm currently the director of the GRASP Laboratory, and I thought it would just be fitting to do just a quick overview of the lab. For I know that some of you are new. So just to give you an idea of sort of who we are by the numbers. So the last number is the most important. The GRASP was established in 1979, making us one of the oldest robotics labs in the country. And we're very pleased to have our founder, Rujna Baichi, sitting right here in front row. So if you haven't had a chance to meet her, please take the opportunity. Currently by the numbers, we're 150 PhD students, 250 plus MSc. And 26 primary faculty, actually it's 27 because we have a new faculty joining us later this year. So that's a lot, but it makes for what we hope you'll find a very stimulating intellectual home. So just a quick overview of mission statement and faculty. So this is a very busy slide where we're trying to fit a lot of pictures in one place. You will have heard and will continue to hear more about sort of what our mission statement is, but basically, we are a research institution. We are here to advance the state of the art in robotics in all of its various forms, whether that's perception, whether that's controls, whether that's mechanism design, and interactions with other units across the university. This is sort of a very, very rough breakdown of some of the areas that we're in. I always say this is kind of incomplete because you'll find many of the faculty will do things that span multiple dimensions. Yes, so for any of the faculty here, I could easily make an argument that they do two or three of these things, but sort of a useful first aspect. Another thing that you should be aware of is that in addition to sort of the primary faculty that I mentioned, we also have secondary faculty who work again across the breadth of the university, everywhere from the medical school, the School of Architecture. We have colleagues in nursing, earth and environmental science, et cetera, et cetera, et cetera. So you will find that there's not very many parts of the university that we don't have some connection with. And I mentioned this in that if you think that your interests are niche, we can probably find somebody that can still talk to you. So please don't hesitate to ask. So with that, let me just sort of jump around and talk a little bit about some of the stuff that I'm personally involved in. I guess whenever I'm asked to explain to myself, I'm broadly interested in perception for robotics. So how do we actually get robots to build representations of the environment from the sense of data that they have, and then make intelligent decisions about what they're going to be doing with it later. So this is just a quick example of a LiDAR mapping system that we did in association with my former graduate student, Anthony Colley, who's, and I guess I won't have time to go sort of through all the details with it, but suffice to say that we were able to develop systems that allow us to represent tens or hundreds of kilometers of area very effectively using these very compact panoramic depth maps. And this has now been deployed. If you go to LA and the really annoying robots that people are like pushing over that deliver burritos, they're running actually aspects of this algorithm. These are other robots that we have deployed in greenhouses around the world that have very interesting jobs. They basically have to walk around many miles carrying things from one part to the other. Usually environments that have little to no cell phone connectivity. So the ability to build compact and efficient maps helps them to get where they're going. So with that, let me move right along here. Go. Okay. The other kind of things that we do, and again, you're going to see a couple of examples of this, so I don't want to steal people's thunder, is we do a lot of multi-robot collaborative teaming work. And this sort of shows up in a variety of platforms. So this, for instance, is an example of the Falcon platform that you'll hear quite a bit about, that was built, again, here at Penn. Building it here enabled us to basically configure this to our liking. So we are in full control of the compute stack, the sensor stack, propulsion system, thrust-to-weight ratio, et cetera. Sort of developed over a number of years through a couple of similarly, this is one of our many mobile bases. You'll find, of course, a number of these in and around, legged, wheeled, and the like. Again, this system is something that we built on top of a mobile base and have been using for a variety of experiments. So let me just sort of show you one of them. This is actually an example of a algorithm developed by students here at Penn, which allows us to localize robots on the ground based on aerial images that they carry overhead. So we can actually do things like fly a drone over an image or over an area, or get a satellite map. And then based on that, this robot that's running around showing the video on the left is actually able to figure out where it is accurately with no GPS. So basically it does that by doing a local semantic analysis of what it sees in the world. So trees, roads, buildings, other things, correlating it to the semantic analysis obtained from the aerial view, which you can see here, where buildings are coded in red, trees are coded in green, et cetera, and basically kind of doing a match to figure out where it is. This is incredibly useful because it allows us to do things like now take multiple robots into the field and have them all register to a common frame of reference, which is important if you want to do coordinated activity and things of that nature. Again, I won't spend my time on this. My colleague Eric Eaton will talk about variants of this that we're applying to the DARPA Triage Challenge, where we're using this to find humans and treat them. This is work of another one of my students, Bowen Jiang. She's currently at Microsoft, working on the latest generations of their LLM products. There's two pieces of her work, one of which is actually generating a text that can be effectively inserted into imagery in a way that is font aware, and other work that she's done on exploring token bias in LLMs and pointing out that actually many of the fallacies that humans are heir to actually show up in LLMs as well, which is another way of thinking about the limits of rationality. Another piece of work that we've been doing, been very interested in applications of deep learning to control. Again, this is something you'll see a number of our faculty working on. And here we're sort of precisely interested in this question of sort of sim to real, and how do we take policies that might be trained with domain randomization and quickly adapt them for the actual platforms that we see in the real world. So this is work by my student, Hersh Sangvi, who will be defending soon. So please come to his defense if you want to hear more about that. A very, 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 very incomplete list of some of the things that I'm interested in, happy to talk more about. Air ground teaming is, as I mentioned, our DARPA Triage Challenge. We have a number of positions that we'll be happy to talk with you about. Vision guided navigation, which I didn't get a chance to talk about, and a variety of other things. So with that, I'm probably over time, but I will pass it over. Okay, excellent.
Hello. So good morning, everyone. Welcome to Penn. I'm Pratik Chaudhari. I'm a professor in electrical engineering. I work on two main things. I work on machine learning and I work on robotics. And I'll tell you a little snippet of both of these. Maybe just to begin, when I was your age, that was many years ago, I was very interested in autonomous cars. So we built some of the first Uber-like systems all the way back in 2011, 2012 style. Some of these were very preliminary golf carts with a few sensors that we rigged up. They later matured into actual cars. If you go to Vegas, Los Angeles, Singapore, you could take a ride in one of these things. This field has obviously matured a lot more since. Today, I don't know if you know, Waymo is mapping Philadelphia, so you should be able to take rides in Waymo very soon. As I began working on these problems, I got a bit more interested in computer vision and machine learning. So those are the two main things that I work on. The first kinds of problems corresponds to theoretical problems in deep learning. This pertains to why do neural networks work well? How can we make sure that we train them more efficiently? You know, all the companies are spending billions of dollars training these models. Saving 2x on it is a big deal. Making sure that neural networks generalize well to new kinds of data. That is the second big question. And the second thing that I work on is mostly outdoor robotics. This pertains to problems of mapping, monitoring, navigation in forests, farms, construction sites. And I'm mostly interested in visual perception, so computer vision style techniques. Just to give you one perspective of how I think of deep learning models are new. We've become very good at using them over the last 10 years or so. They aren't very different from the other models that you have in scikit-learn. They are bigger, they have little more delicacies, but the basic tenets of what makes machine learning work also makes deep learning work. And what is oftentimes lost in the conversation is that machine learning is fundamentally about modeling properties of natural data, natural images, sounds, text, olfaction, audition. And at the end of the day, we think of models as making predictions on the data, but the goal is to understand this data. And a lot of the properties that make neural networks so miraculously successful actually seem to be coming from typical properties of the data. And one very simple thing to appreciate is as follows. So images, your phones, for example, take images of maybe 40 megapixels, 50 megapixels, depending on your phone. That's a heck of a lot of pixels and a lot of bits, right? Images have nowhere close to that amount of information. The typical number of dimensions in an image is more like 100 because there is so much redundancy in the image. The red share has red pixels all around, so doesn't make a lot of sense to worry about all the individual red pixels. And this low dimensionality underpins the success of all machine learning models, including deep networks. Deep networks are a little bit more cool at exploiting these kinds of structures. Okay? And what we have found over the years is by looking at these properties, we can train neural networks. So we have some of the fastest methods to train neural networks, some of the best algorithms to train them on different kinds of tasks in visual recognition, continual learning kind of problems. We can do these tasks with very, very few samples, so more like 5 labeled samples per problem. One very dramatic example of this kind of property in deep learning is shown in this picture. I won't explain you the picture, but I'll tell you the gist. Neural networks have a lot of weights, okay? There's 50 million weights, 1 billion weights. The largest ones is 1 trillion. Turns out they actually need not have that many weights. You could do just well with 50 coefficients, 100 coefficients, and you would get the same performance. Now, we haven't managed to find these very small networks yet. But when we do, we should be able to get them, we should be able to get much efficient machine learning. The second kind of problems that I work on corresponds to mapping in large regions. While cities are very structured, things like forests or farms don't have as much structure. They don't have people who move around, but they don't also have that much structure to benefit from. So we've become good at, over the years, using some of the drones that CJ showed just now, traveling for multiple kilometers, building maps. So for example, if I tell you now, go to the medical school, half of you do not know where the medical school is. We have systems that would build a large enough map and explore it by itself. Let's skip this one. The second kind of result that I wanted to emphasize, and you'll hear more about this very soon, Fernando will show you. Some students of Kostas Daniilidis and CJ Taylor and Vijay Kumar built this data set across different kinds of platforms, cars, quadrupeds, flying vehicles. What we have been doing is working with a special kind of camera. This is called an event-based camera. And Kostas might tell you a bit more about this in 2 minutes from now. These cameras, your standard camera creates a frame. It gives you the entire image at one go. Event cameras only give you which pixel changed at which time instant. So at pixel X, Y, at time T, the intensity increased or the intensity decreased. That is the only amount of information you get. And these are all the little white dots on the top right image. What we've built is good machines to understand representations of these sensors. Because they're so very different from standard cameras, you really need to do computer vision from ground up. And all computer vision algorithms need to be thought a little bit differently. So these are two simple examples of the kind of things that I work on. Please feel free to reach out. I look forward to seeing you in courses and seminars across the next 2 years as you enjoy Penn. Thank you.
Share my window. Get there with that. Is that your presentation? Just share that and then hit share. And presentation. All right. So my name is Kostas Daniilidis. I have been Penn since 1998, and I teach the machine perception, which is about geometric vision class 5800. What we see here is one of the most advanced models from industry, from physical intelligence, the Pi-0, which has given the language command take the spam can and put it into the tray. And you see that it fails by bouncing really the spam box onto the disk tray. Then in this example here, again, it manages to capture the command is to put the glass bottle into the bowl. And here again, actually, it does not have a good representation of the environment. So it bounces the bolt again on the bowl. And this is a system that has been trained in millions of examples where the input is a language command and images from a camera on the wrist. And output is really a sequence of actions. And what we want to argue is that a robot needs really very good representations of the environment. And also it needs a very good way to reason then about the environment. So in order to build these representations about the environment, the current way of doing things has been based on Rick Sutton's bitter lesson article, which was saying that whatever actually geometry or physics knowledge you try to put in a machine, it does not matter. The only thing that matters is really the size of your training set. We have been working against this lesson for many years. And 2-3 months ago, Rick Sutton, Turing awardee, together with David Silver, they actually published an article which is, they really argue that the bitter lesson is over and that we are entering the era of experience where a robot is not just trained in millions of demonstrations, but is learning from its own work, coming back again on the reinforcement learning techniques that were not really used in the current models. Now, we argue that if you want to experience the environment, you really need first to actively look in the environment. And this is based on psychology theories that a camera is not a device that really just perceives passively. The eye is really looking around and has a way over this sequence of views of the scene to build a very good representation. So what we have built is first a system based on information theoretic tools that when we want to have a 3D reconstruction of the environment, we don't take just 200 views, but we want to take the best views that will maximize the quality of reconstruction. And we expanded this into a system which has also incorporates on top of the representation of the environment, the views that will maximize the quality of the grasp. And this is like a situation where we try to grasp from a very occluded area, the red cap, and we are able to succeed because we have a very good environment representation as well as very good affordance representation on how something has to be captured. And we continued this work also on navigation. What is the best views in order to explore the environment based on the very basic idea that we have to take views that will surprise you. And looks that will surprise you is the one that you cannot really predict, where actually your PSNR, the quality measure of the construction, when it is low, then the information gain should be high. In general, look for areas where you don't have, where you cannot predict what we're going to see. This is our main paradigm now, both for manipulation and navigation. We have worked on many other geometric problems. In this case, we have a simultaneous solution of the slam problem for the camera, as well as the 3D human motion reconstruction, as well as on the full 4D reconstruction from videos, which really should be used when we try to predict the environment, not only with 3D point clouds, but with full 4-dimensional trajectories. And I think I'm going to stop here. You can see the rest on our website. Next.
All right. Hi, everyone. I'm Eric Eaton. What I'm really interested is systems that are deployed for really long periods of time in an environment. Things that, for example, could live in your home and do whatever you want. Long-term adaptive systems that can really be customized to exactly your needs. And so my research looks at this from a variety of different perspectives. The biggest one is lifelong learning. How do we take systems, deploy them for really long periods of time in the environment, and have them build on their knowledge? Consequently, we're also interested in open world learning, where the world is not defined and we have to learn from it as we go along in order to experience things. I'm interested in systems that collaborate interactively with other agents and people. And finally, a lot of things we've been doing is building on these recent advances in visual language models to create multimodal large language models to realize some of this. And my work applies this to problems in robotics and medicine. So I'll talk about a few of these. So an example of what I mean by lifelong learning, here we have a robot that we've trained to do pick and place. Now we take that same system and change something about it. In this case, we're using a different arm. And then now we change the task. Now we have to drag something along the table. Then we change the object. Then Instead of that, we add obstacles. And you can obviously see that we get a giant combinatorial explosion of these things, of all the different combinations that we could do. And what we really want to do is develop a single set of models that are versatile for all these different tasks and can learn on the fly. So here's an example of one of our lifelong learning systems. This was deployed during a live demonstration during the ICRA 2022 conference, which was held in Philadelphia. During the conference, we had the robot moving continually around the environment and learning essentially where it could navigate the space. And this was the first example of a real-time lifelong learning, to my knowledge. And periodically, we had the audience try to fool it by rearranging the room, introducing new objects, and so forth. And what it did was it built on its experience over time to get better and better. One of the examples of types of problems that we work on is how do you take algorithms that are intended to interact with the environment for a long time and actually make them robust and make them work in practice. And so RL is an excellent example of this. What we typically do is drop a robot in an environment, sample a bunch of trajectories, and learn a policy from that. And then if you repeat that same process, what you might get is a completely different policy because you're sampling from a stochastic environment. And in papers, it looks like this nice plot over here, everything's nicely average. In reality, you've got this weird combination where some of the runs look really good, other ones look really, really bad. And so what we want to do is figure out how can we float along kind of the top of all these? How can we get the best performance as we go along, yielding robust and replicable policies? And we've developed a series of algorithms that do this and released it. Next problem I'm going to talk, jumped ahead. Next, I'm going to talk about is the DARPA Triage Challenge. So DARPA has run a series of robotics challenges in the past. This is the latest one. The basic idea is some mass casualty incident happens. This could be an earthquake, a shooting, a chemical spill, something along this line. First responders roll up, press the big red buttons, and off go the robots. The robots find all the casualties, locate them, and triage their injuries to allow first responders to best prioritize their resources. And so these are examples of our robots and our teams running the triage challenge. So this is from year one. Here's examples of our robots. We have four jackals and one quadrotor here that was developed in-house. Here's a video of our most recent run of the competition. Everything is fake. It's all Halloween makeup. You will see blood and such though. So here's our quadrotor in the air. You see it's a battlefield scene where there's smoke. The robots are going around from casualty to casualty. It's a mix of mannequins, like animatronic mannequins that kind of move and twitch, live actors, and still mannequins. That would be, for example, a dead body. And our robots going up, finding each of the victims, and triaging their injuries. So this is really a combination of like fundamental robotics in terms of mapping the space, learning models to recognize what the robot is seeing in terms of the injury patterns, and then communicating that to first responders in order to allow them to best prioritize the resources. At the heart of all this was a multimodal, a visual language model that did a lot of the triage for us. We've also been using multimodal large language models in other contexts. For example, in this case, where we're learning from video or image information to full URDF articulated models to figure out what the affordances are of the object in order to allow us to interact with them either in simulation or in real world. Or going from raw pixels to developing full physics-based models to really understand how the world moves to allow us to interact with it. Again, all of this is under the guise of learning affordances for understanding the world. And the last set of problems that I work on is how do you take and develop ambient AI systems that can actually be rolled out in the clinic, where in this case, we might have a physician, a patient, as well as the AI system all acting as a collaborative partner. And so we've gathered up a bunch of real data from clinical encounters at Penn Medicine and are in the process of learning multimodal models to allow us to do real-time patient assessment as well as completely document the visit, allowing the provider to just pay attention to the patient. We've been doing a lot of work in different areas, everything from gait assessment to understanding spatial temporal clinical interactions. And I want to highlight one thing. We have a new grant that was just funded on developing clinical multimodal foundation models. So if anyone's interested in this, please come talk to me. We have opening, want to acknowledge my students, past and present. And if you're interested, please join us. The application's up there. We're especially looking for people to participate in the DARPA Triage Challenge, as well as develop the multimodal foundation models for clinical environments. Thank you. Thank you so much.
Hello, hello. Oh, should I try this? Well, yeah, I'm the dog. I'm Momo. So I've been here a long time. Someone, CJ mentioned 1979. Actually, I came in 1978. So I remember when Rogina with Aravind created the GRASP lab, although in those days, we were on the same floor. She was at what end? I was at the other end. And I was really, it was my, as I say, my first love, namely logic and computability. But I got perverted later on in the mid-90s. And then that's when I started working on more geometric sort of issues. So let me give you, so I have many interests, probably too many. How do I call that? Oh, sorry. And in my old age, oh yes, so it's hard to tell how old I am, but I'm actually very old. I'm a cousin of Dracula. So I'm really a vampire. So don't bug me because you will regret it. Okay, yeah. Regina knows that, you see. She's a vampire too, I suspect. But anyway, so okay. So I've written many books. I have many interests. As I said, my original interests, which are still current, are mathematical foundations, logic, lambda calculus. And when I want to understand things really in depth, I write. And I suggest you do that. I have a feeling that most students these days don't read. In my classes, I discovered that. I'm completely shocked. They watch videos, do. Okay. So yeah, it's very cute, but this is not really the way you learn in depth, right, Regina? No. You've got to read because your system reads and, you see, okay, I'll prove that. Okay. My cheap, little talk there. Okay. So occasionally I got completely perverted. Well, I got offended. I hear things I don't understand. People tell me things and I have no idea what they're saying. In most cases, the reason is that they don't really understand well. So they don't really explain well. At least that's my impression. So I want to understand. And then I launch into things. So homology, cohomology was one of these things that, and I came out of it. Okay. Now, about 6 years ago, across from my office, which was at 476, there were students, and I kept hearing them talk about Fourier transform, hard measure. And I said, ooh, I know something. So students of Kostas. And so we had for a year, we had this sort of underground meeting. We were meeting, yeah, it was not underground because it was on the floor level, but we read books and I explained the hard measure. That's why I have some gray hair and lack of hair in the back of my head there. And anyway, following my recipe, I wrote about it. And so I have these 2 books. So I've decided to put all of my stuff online, all my books, all the PDF are there. Too bad for you, okay? And actually, something very funny happened. So people send you mail occasionally and they say, oh, Jean, and they say, Jean, oh, okay. I love your stuff. You put your stuff there free, but why don't you use hyperlinks, hyperref? You click, 2, theorem 3, 4, click, okay, 2, okay. So, no, that's okay. That's all right. So anyway, I hyperrefed everything. So it's really wonderful. And the dog helped me with that. It was really, yeah, he sits there and he barks, occasionally when there's noise in the street. So these are the books. And by the way, so World Scientific, someone likes me there. And so they asked me if I was interested in being on a book series. So if you're interested in publishing, you should, okay? It's painful, by the way. It will suck you in. Very painful to read books. Yes, because you can't think of anything else, basically. You have to keep the whole thing. And then there's the minutiae, the commas and the struggling with LaTeX and displaying, beautiful sigmas and pi's and Greek. But /BM. What is that? Bold Greek. It makes hyperf crash, by the way. So anyway, so I was going to tell you, but I think that it's probably not really necessary to do that. I was going to tell you about the Fourier transform. I'll just tell you. So I got very obsessed with the Fourier transform. So, on the circle, right? You integrate against, f of theta, e to the minus m theta. So what the hell is e to the minus m theta? Well, it's a function, right? You give it a real number, done. Ah, close to done. Okay. The vampire will take its revenge. Be careful. Okay. No, that's right. So fantastic. You integrate, you get the coefficients and you reconstruct. But suppose this is not the circle. This is, the group of rotations in 3D. So you have to be able to compute Fourier coefficients on a group. So you have to know how to integrate on the group. And you don't get coefficients, you get matrices. You get a set of matrices. The reason is that you have to replace these e to the minus m theta by representations, but I probably ran out of juice here. So, woof, woof, okay. That's the dog. Momo, that's the dog. It was close, by the way, almost did not connect them.
Good. I'll need to hold the mic, right?
Sure.
I am, yeah. All right. So I share one similarity with Jean in that I also don't know how long this is going to take, but I will only aspire to be as interesting as Jean. So I might not be quite as entertaining, all right? So my talk is going to be about the work that we do in my research group on robot learning. And in particular, recently, I've been thinking about the work that we do as falling under two categories, exploitation and exploration, that together, I hope, will help us engineer better robot learners. Okay, so over the years, I've been around at Penn now for 5 years, and we've developed several techniques for teaching different classes of robots, quadrupeds, as well as manipulators, and more recently, even quadrotors, to perform various interesting skills. We've gotten quadrupeds walking on yoga balls, doing all kinds of circus tricks, and so on. And one way in which we've been kind of making progress on things like this is in the last couple of years, we've been really exploiting the rise of large pre-trained foundation models to advance imitation learning, sim-to-real RL, the techniques that have been working really well for robotics recently, to get policies, rewards, representations, and more. All right, I'll tell you a little bit about projects in the last year. This one is about an example of using foundation models to directly distill policies out of human data. So what you're seeing on the left there, if it was playing, was videos of humans performing various tasks in their homes and so on. And how can we actually learn something from that can then transfer directly onto the morphology of a robot? In fact, if you're learning something from human videos, it might not even apply to, it might not be specific to any one category of robots. So it will even apply to new robots like you see on the right here. It won't be specific to any one scene that you're training the robot in because you're actually training it on all the homes of all these people. And that, it turns out, is a nice way to think about how you develop generalist robot policies. And so we've been making some progress on that front. The references for all of this are along the bottom, okay? Here is another example, even more recently, in just the last couple of months, of foundation model-driven policies that are created by abstracting the scene into a key point-based representation. And it turns out that computer vision has made a lot of progress on correspondence finding once you reduce a scene to these key points. And it turns out that that is a really good representation on which to learn policies from a very, very small number of demonstrations. Like 1 to 10 demonstrations is sufficient to start learning policies that will then actually generalize in some way. And that's what you're seeing on the left there in that time lapse, is a policy that's trained with as few as, I think, 10 demos, and it's able to perform these various tasks. And it turns out that that's a good way to then bootstrap data collection for performing more complex tasks, like things like this coffee cup insertion that you'll see on the right, which is a really kind of very tricky, finicky, precise insertion task. And hopefully, if the video plays out, you'll see just settling into place the little coffee pod. All right. I'm going to wait a couple more seconds. I'm losing time here. All right. Good. And then here is another example of not getting policies straight from foundation models, but instead using foundation models as ways to derive rewards for something like reinforcement learning. How can a foundation model tell you when you are succeeding in making progress towards a task? To what extent are you succeeding in making progress towards a task, etc.? It turns out that, again, abstracting things into key points and then using correspondences is a good way of performing this kind of feedback computation. And it turns out that that can then inform the learning of policies in the real world from just having a human demonstration to tell you whether or not you're making progress towards the task. And so the policies that you see along the bottom are policies trained using those foundation model-driven rewards. Here is another example of foundation model-driven rewards, but actually not just rewards, some domain randomization parameters and more, like design choices that are often made for training robots and simulation. It turns out that you can actually get a VLM together with a search process to make several of those design choices without requiring one of my graduate students to spend months doing it, which they're all very happy to try and delegate this task to these VLMs. And it turns out that that kind of laziness led to really cool results. We have been getting these robots. Sorry, my videos are a bit wonky. I think I might have put a few too many of them. Let me see. All right. If I can get these quadruped robots to play. Okay, yeah, there you go. Here is an example of some skills that we train for a quadruped to perform essentially parkour style obstacle course navigation. And more recently, we've also even gotten foundation models to produce scene representations that look a little bit like what you see along the top, where you decompose a scene into its most task-relevant entities. You focus on the objects that are particularly relevant to that task in more detail. You decompose it at finer levels of detail. And that, it turns out, can also inform very fast imitation learning. So essentially, the idea here is that foundation models are offering useful priors to operate either zero-shot or with minimal fine-tuning in new contexts. But having gotten all these cool video results, we have been, these cool kind of robot demo results, we've been thinking about where the limitations of just simply scaling today's techniques lie. And one of those questions that we've started to focus in on is resource inefficiencies. We think this is kind of very foundational to robotics, that we should be thinking about what can a robot operate, what can a robot possibly do under some specific constraints on various kinds of resources. And so one way to think about that is that we should be both exploiting as well as exploring better. We should be exploiting today's best approaches at not just the limit of infinite scale, but across various resource budgets. And we should also be exploring better to get better, more fundamental design principles that can actually inform our designs. I'll kind of skip this slide. We've been asking questions like, what must a robot learner attend to at each stage within the process of computing the actions from sensors in order to learn and perform a task? And how does that vary as a function of the task and agent characteristics and the learning phase? And towards that, we've been pursuing this all across the control stack. We've gotten some cool results in the last year. These are really foundational questions. And we don't have as cool robot demos for most of these works, but I think of these as things that will inform the robots of the future, capabilities for the robots of the future in 2 or 3 years from now. We've begun to get a sense for when, at which moments in time, which sensors are required for a robot to learn and perform a task, and what kinds of representations do they need, and so on. And they're beginning to drive cool robot results as well and come out of simulation onto real robots. So with that, let me thank the group that actually worked on this, as well as the funding agencies, and I will pass on.
Let's see if this works. Come on. Oh, I guess Zoom died. Great. Let me get the link. Sorry about that. I had it ready to go. I guess I was too excited about it. Right. Anybody see my screen? Good. We're gonna make these small so it doesn't bother us. And I think I'm ready to go. Okay. All right. Hi, everybody. It's great to see so many people here. Believe it or not, I was a student a few years ago, and I was on your side.
And this is a great opportunity to see all the amazing research that is happening here at GRASP. So I hope you can enjoy these sessions, and why not like join some of the labs. My name is Fernando Cladera, and on behalf of my colleagues at Vijay's Kumar's lab, presenting some of our research and some of the cool things that we do in the lab. So first of all, let me introduce the whole team. So we're a lot of folks. A lot of us are co-advised by other professors here at GRASP, but we usually meet on Fridays at Pennovation. Most of us, or a good chunk of us, sit at Pennovation. I guess you guys visit for the barbecue. So it's a great place to do field robotics. If you haven't been to Pennovation, I highly encourage you to go and see the buildings, see the places where we can do field experiments. But we're not also only people, we're also a lot of robots, as you can see in this slide. We have robots that go from wheel robots, quadcopters, as small as 50 grams, up to 4.5 kilograms. That is around 9 pounds in freedom units. Leg robots, we have started recently using leg robots. And something you can see is that all these robots are outside. They are experiencing the real world and facing real world challenges. And this is one pattern that we observe a lot in our lab. We try to do realistic experiments with robots in real world settings. So I'm going to start talking about motion planning. Some of this work is led by Yue, Jifei, and Yueshan. And why motion planning is challenging in quadroros? Well, because these are like constrained platforms. You are constrained by the weight. That means that you're constrained by the computer that you can put on board, but you still need to do this motion planning in real time. Because otherwise you're going to crash with something. So here you can see some examples of this motion planning where you have dynamic obstacles moving around. And UA is also focusing on like how could you use neural networks to optimize trajectory planning, such as how to use it for optimizing time allocation. That means when the road needs to be at what particular point in time. You can see some of the videos of these experiments here. But also they have been focusing on how to do flight in very, very cluttered environments, such as the ones you can see in these videos. So for instance, if you want to fly a quadrotor in a forest, how will you do that? So these are some of the examples of the research that they're doing. And finally, multi-robot coordination. So if you want to track a ground robot with your quads, how you can do that in a robust way, as you can see in these videos. So I'm going to jump to some of our projects on the wind estimation. Spencer is the main researcher working on this. So why it's important to estimate wind in quadrotors? Well, because you can avoid dangerous situations. If you're flying your quadrotor, let's say in a city, you don't want to put your quadrotor in a difficult situation because there is a gust of wind that can like make you crash. But also you can harvest the wind energy to fly better, to fly more efficiently. So in this little video, you can see how as he's moving the quadrotor along this scene, there is a wall of fan that's like blowing air to the from the bottom to the top of the scene, and the quadrotor is estimating the wind components, and it's also estimating the distribution of the wind around it to fly more efficiently and avoid dangers. Up. We also have We also have do a lot of research on agricultural robotics. So as you can see in this video, we're flying on a clutter forest. While the robot is flying in this environment, it's avoiding obstacles such as little branches and the undergrowth. And at the same time, it's constructing what we call a metric semantic map. That means it's mapping the locations of the trees in different locations, and it's also estimating diameters of these trees. Also, we have done experiments in orchards where we're estimating, for instance, the size of fruits, the locations of fruits, and so on. And we have a recent paper that was recently published where we not only estimate the location of fruits, but also estimate, okay, come on. We also estimate the location of fruits and how they grow with time. So we can track these fruits along a particular growing season. This work is some recent work that we have done in collaboration with Zach. He's going to be talking a bit later. So cool things here is that we have a team of ground robots and air robots working collaboratively to explore a big area. So in this case, one of the mission examples is that there is a chemical spill. So the ground robot is going to be tasking a UAV in real time to build a metric semantic map of the environment. So all this is running on board the UAVs while they're flying. As the UAV is flying around, is building this map, transmitting this map to the ground robots, and the ground robots are using to validate some of these objects of interest. All this is happening in real time. So we do experiments with multiple robots in the field. Finally, I'm going to show some of the research that I'm doing with event cameras. So here is a sample of a street in Philadelphia. You can see that it's Philadelphia because in the street, you not only have cars, but you have a horse, you have a person with a forklift, and then you have a bike that is crossing in front of the camera. Yeah. And what event cameras can give us in these realistic real world scenarios. I have another clip here of event cameras flying from a UAV. And the interesting thing about this is that event cameras can recover information that traditional RGB cameras lose due to like high dynamic range conditions. And we can build some of these maps that overcome these problems. So to finish, as I said, this is an overview. We have many, many projects. If you scan this QR code, send me an email. I will keep you in the loop. So it'll be great if you can join us. We have many projects for master students, first year, second year master students. So it'll be great if you can work with us. So thank you so much. One more thing. I know you like videos, so go check our YouTube channel. You get research overviews in 3 minutes. So no need to read papers. Thank you.
Okay, looks like this works. Hello, everybody. My name is Antonio, and I'm assistant professor here in the GRASP lab. My main interest is learning from synthetic data. Specifically, how do I get an imperfect model of a complex system and use it for taking decisions in the real world. This is usually called simulation to reality transfer. The idea, I guess, for many of you, you have already heard about this before. You take something which is a really poor representation of the real world, and for some reason that we don't yet very well understand, we can train policies that actually work there in complex environments. The problem, though, is that as a practitioner, that's what you probably think that sim2real is. You have a simulation, you have the real world. Those things are not exactly equal. So you run some tests, you collect some data, you improve your simulator, you do some tricks, you do this over and over, and here you go, you get good performance. This is unfortunately a mistake. Sim2real is unfortunately a very hacky and painful process, which involves a lot of painful calibrations, infinite long config files, identifications of things that are actually impossible to identify. So it's a set of hacks. There are only few labs in the world that can do this effectively. And what we're asking ourselves is whether there is a better approach for doing this. So most of my research has gone into this, how to use imperfect simulators from the start instead of doing all that painful process. And of course, this has many prospects, like, for instance, be able to learn from other kind of imperfect simulators. You can, for instance, think that humans are, as a matter of fact, imperfect simulators of robots. Okay, so just to give you a very quick overview, if the next slide works, here we go. So I've been working on this problem right now, like for several years, and that's kind of my main research direction. I've been studying a little bit of the trade-off between the two things. Of course, as the simulator gets worse, you will need like more data to adapt. In the case of drone racing, for instance, you can model stuff pretty well, and you only need very limited amount of real-world demonstration. But interestingly enough, for instance, for legged robots, even if you don't have a good simulator, even if you simulate a camera as a simple 4-point detection distance algorithm, turns out that with very little real-world experience, you can adapt. We have been now extending this to even more complex systems, like for instance, manipulators, I've just seen it before. And something that I'm really interested in is studying the limit of this paradigm. What happens as the simulator gets very bad, like for instance, for simulating something big, like a wind farm or like a massive airplane. What happens? Are the data requirement in the reward be exponential or are gonna flatten out? And is there a unified paradigm? Can we stop like doing all this set of hacks? Okay, so this is more or less kind of what we do in our lab. But I see many new faces here. And what I really want to do is to show you what you could do in my lab. And not using my words, but actually asking some of my master students to come in and explain you at very high level what they are doing. So I'm first going to start with Margaret. Yes, please come.
Hello, my name is Margaret. I'm currently a second-year Ruble Master working in Antonio's lab. And okay, actually, yeah, the project that I'm working right now is kind of a motion capture suit. As you can see here, this kind of a very fancy Boston Dynamic motion capture, which you can, like by wearing a VR glasses and holding some haptic controller, you're actually teleoperate a real humanoid here. You can collect very high quality data. You can train your robot with that. But actually, they have a lot of problems. As you can see, it's actually pretty expensive. And also, you can see the third-person camera there and also some tangled wires. It's actually limited in the lab and with very limited freedom of movement. What we're trying to do is we're going to build a kind of a motion capture suit, which with very cheap IMU, maybe just $20. And we have this kind of area glasses. This kind of IMU, it's cheap, but it's actually pretty good at capturing your body motions, and the area glasses can offer you some localization and some RGB information. And as this demo, you can see I'm actually catching a ball, and yeah, so with all information, you can do a reconstruction and also the retargeting. Yeah, it's actually working. Yeah, that's kind of my program.
Nice. Next, I'll have Jefferson.
Hello. Hello, thanks. I'm 30 seconds. Okay, so this work that I've been working on is quite different from the normal works. We are basically building a survival robot, and it's a scientific exploration into what a simple reward like keeping a battery charged can really do to complex behaviors emerging. So we build this survival robot, give it as much sensing modalities as it possibly need, and we just deploy this in the forest for not just hours, weeks, months probably, hopefully. And we hope we can get a glimpse of intelligence emerging by the end of this project. And I think this will change robotics research. Thank you.
And I'm gonna finish up with this master student, like Vinette, is working on multi-agent racing. Unfortunately, couldn't come because he's now having a PhD interview. So, well, if you like this, please get in touch. We're always looking for people. And yeah, thanks for your attention.
Sorry? You gotta share screen.
Let's see.
Great. This is the mic. Perfect. Hey everyone, I'm Zach Ravichandran. I'll be presenting on behalf of George Pappas and giving a quick overview on some of the directions in the group. It's a list of current members, fairly large group with varied research directions across control theory and robotics. I'm going to spend most of the time highlighting a few of the key directions in the robotics fields, which I've listed here. And so on the top left, one of the big directions of the group is asking more theoretical questions in learning for control. And this is looking at typical learning pipelines where you get a robot, you collect data, you try to fit some controller, some model, and it's trying to ask fairly fundamental questions on if you're trying to learn a policy for control, how much data do you really need to be optimal? What are the safety guarantees that you can put on your controller? What are optimal ways to collect that data? This is some figures from a project on looking at domain randomization critically, for example. Some other work on multi-robot systems. And so I have on the bottom left some work in collaboration with a group from Portugal on environmental monitoring. And so in this project, there's a team of underwater autonomous vehicles, and we are trying to create planners using reinforcement learning for monitoring characteristics of the ocean for environmental protection and similar problems. The top right, there's a lot of work in collaboration with Vijay Kumar's group, similar to what Fernando just shared, on semantics-aware robots. And so this is saying, can we put, related to a lot of the work, the foundation model-related work, language models and vision language models, can we use those to create closed-loop planners that can reason about language-specified tasks, reason about the semantics in their environment, and plan in a safe and robust manner. And so we've deployed these on drones, on ground robots. We're moving towards also teaming directions with these. And finally, we've been doing recently a lot of work for safety in LLM-enabled robots, and I'm going to spend the last few minutes talking about what that work looks like in particular. So the primer on LLM-enabled robot safety, I've been making big splashes in robotics. I've been pretty quickly integrated into a lot of both academic and consumer-facing platforms, like I've displayed here. That's great. I think there are a lot of really exciting reasons why people want to do this, including our group. They primarily enable a natural human interface and this notion of contextual reasoning. So instead of having to design a very specific controller for a specific task, a person can give some language specification. Here, like, can I cross a river? And you can use some of the reasoning of the language model to do, most likely actions. So let's say I'll look for a bridge if I want to cross a river, similar like that. Kind of due to the underlying vulnerability of language models, this can be hijacked. So if a malicious actor, for example, says disrupt the fire drill, a language model will say, okay, I'll go find an emergency exit and block it. And they're kind of a host of behaviors that emerge when you start to put foundation models into robotics. And so we have a line of work studying this. What we call jailbreaking is trying to document and characterize what are the safety vulnerabilities when you put foundation models into robotics. This is some work that we presented a few months ago on looking at GPT and similar models here. And now there's a line of work on, okay, now that you say you have language models in robotics, they have these safety vulnerabilities. How can we prevent safeguards to address them? So I'll end with that. Any interest or questions about this work, please feel free to reach out. If not, thanks for listening.
Hello, everyone. My name is Daniel Feshbach. I'm a PhD student in Cynthia Sung's lab, and I'll be presenting on her behalf because she's not here today. So in the Sung Robotics Lab, a core unifying theme for a lot of our research questions are how can we think more formally about the role of geometry and compliance in robot design and their relationships to robot functionality. We have a bunch of different projects in our lab that fall under this theme. Many of them relate to the computational design of robots, to planning for multi-robot systems, to the design of robots to leverage compliant mechanisms, and also to fabrication based on origami structures. So here are some of the specific research questions that we're interested in. One of them is how can we leverage soft structures and multi-robot interactions to achieve energy efficient locomotion? In this slide, what we're seeing here on the top is a project involving the Liebau mechanism, which is a way of basically rapidly vibrating and pinching a soft tube in order to induce fluid flow through the tube, which on the right, we have a first prototype of a robot that's swimming using this mechanism. On the bottom, we have, this is a project inspired by an organism called SALPS, which is an underwater jet-propelled swimming robot. No, sorry, swimming animal, which we're building robots inspired by. And SALPs are very energy efficient at their being able to travel long distances, in part because they gather themselves into these long chains where the bunch of them are attached together. And so we're studying with robots how we can attach multiple jet-propelled robots together and ways to time their the respective jet propulsions and to achieve hydrodynamic efficiencies. So on the bottom right here, we have some data we've gathered from using lasers to measure fluid flow and vortices when multiple robots are propelling in synchronized ways. Another research question we have is how can we enable algorithms and interactive design tools to design robot mechanisms? So specifically, a lot of this is about designing the kinematic linkages for robots, and doing so in a way that we can then attach them to fabrication scripts we have to output the design files to manufacture those robots out of either tubular origami or 3D printing. We're also interested in how we can integrate electronics and smart actuators directly into compliant mechanisms. A lot of this is based on also based on origami-based fabrication, because the idea there is you can use efficient planar manufacturing techniques to directly embed the electronics while you're while you're attaching everything flat, and then flat structures can fold themselves into complex 3D shapes. So here we have a robot that is, its main body is made out of a flexible printed circuit board, in which we've made a series of cuts to induce bending and folding. On the left, it's actuated by a servo we attach to it, and it's actually able to both crawl forward, fold itself into shape, crawl forward, and even steer left or right based on just the one actuator. On the right, it's actuated by a new type of smart actuator that is developed by Xu Yang's lab in the material science department. We're also interested in co-designing the hardware and software for distributed control of complex and redundantly actuated systems. Here, for example, we have these loops of material that's based on how much plastic we spool into the loops. We get different amounts of stiffness in the sides of the robot. And we also have tendons running through the robot in various ways. And so by combining ways to pull on the tendons and manipulate the stiffness, we can get a series of these to move in a lot of different shapes. And having this sort of hyperactuated, redundantly actuated system lets us balance different kinds of objectives. Finally, we are applying a lot of these ideas to multi-robot systems. This is a project with NASA in a collaboration with a bunch of other labs, and where the idea is that robots on extraterrestrial bodies will encounter lots of difficult terrains, and when we have teams of them, we want to be able to connect them with with a network that of basically tubular structures that lets them push and pull each other to overcome obstacles. Like this one here is the middle one is getting stuck on this sand, but the others are helping it overcome getting stuck. This is our lab. Please check out our website if for more details, and contact Dr. Sung if you're interested in what we work on.
Okay. But wait, there's more. Not today though. I want to remind you guys to come back next week, Friday, where you get sort of the second half of projects in the lab.